so on 5.1, we're still dealing with integrations. All of chapter 5 will still be dealing with integrals. Okay, so on today's, we're dealing with integration of answers that would be natural log. So just as a reminder, what was the derivative of natural log?
U prime over U.
Okay, good. So natural log absolute value of u was u prime over u. Okay. So when you do integrals, if your integral is in the format of u prime over u, so you have a fraction, the derivative of the denominator is on the numerator of the fraction, then its antiderivative is a natural log. So that's what this first one is showing. If I had 1 over x dx, well, the derivative of x is 1, and that was on the top of the fraction. So this is the derivative over the original function. So the antiderivative of this would be natural log absolute value of x plus c. Now, the reason they're putting on the absolute value, because the derivative of natural log of u, even if it didn't have an absolute value around it, is still u prime over u. The reason the absolute value has to go on it when you do the antiderivative is because the domain of a natural log function. The domain is 0 to infinity with a parenthesis at 0. You can't let the denominator be 0. So with the natural logs, when you do the antiderivative, you put the stuff that was on the denominator, that u, in absolute values just to force it to be a positive, because that's what the domain of a natural log is. You have to have natural log of positive things, not negatives. So make sure to put those absolute values on. And then plus c because of the constant. Okay, and then if you do u substitution, your integral might look like 1 over u du, or you could write that as du over u. Either way, that integral would be the natural log absolute value of u plus c. So the key thing today on your assignment is just see if the derivative on the bottom, if the bottom of the fraction, if its derivative is on the top of the fraction, then it's natural log. Now, you do have to have that memorized, because I do see students that will try to do this by adding a power and timesing by the reciprocal. So if I tried that, if I took this right here and moved it up to the top of the fraction and rewrote that as x to the negative 1 dx, if I tried to then add a power and times by the reciprocal, yes, I'd have x to the 0, and then the reciprocal would be 1 over 0, and that's undefined. So you can't do these by hand the way that we were doing them second quarter. So you do have to have it memorized that it's natural log absolute value of u plus c, because you can't do it that way. Okay, so the guidelines, it says memorize a list of basic integration formulas. Find integration formula that resembles all or part of the integrand. Choose something for a u substitution. So some of them on your assignment today, you'll be doing u substitutions, but you don't have to do it on all of them. If you can't find a u substitution that works, try altering the integrand. So that might be try doing long division, try factoring it, see if you can cancel things. But try to change it somehow to get something that would work. Okay, so this first one, the integral of 5 over x dx. You're close with the natural log absolute value of x, but what do we do with that 5? 5 natural log. Yeah, because that 5 is just a constant. That 5 I could have pulled out in front of the integral and wrote that as 5, the integral 1 over x dx. So now the derivative of the x is 1. And so I know the antiderivative of 1 over x dx is the natural log absolute value of x. But then since there was that 5 on front, I have to then times by that constant. And then don't forget your plus c. Okay, so on the next one, again, that 2 is just a constant, so I could pull it in front of the integrand. But my problem is if I did the derivative of 5x minus 1, what's that derivative? Okay, but on the top of the fraction, I don't have a 5. I have a 2. So I could just do a u substitution if I wanted to. I could say u is 5x minus 1, and then the derivative of that is 5 dx. And so that 5, since it's not appearing in the problem there, I can divide by 5. So I can now replace the dx with a 1/5 du. So this 2 that was a constant, I can pull that in front of the integral. And then this 1/5 du That 1/5 goes in front of the integral also because it's a constant. And then the dx also goes away, and that becomes the du. So now I'm going to be left with 1 over, and then the 5x minus 1 becomes the u. Now the 2 times the 1/5 is the same as 2/5. So I can just write that as 2/5. And then 1 over u du, well, the derivative of u was du, so this is like having 1 du over u, so this is natural log of u when you do the antiderivative, plus a constant. Yes, it's a natural log of u. Okay, and then from here, with your u substitution, you don't want to leave u in your answer, so then you just substitute back in what u was, which was 5x minus 1. So 2/5 natural log absolute value, 5x minus 1 plus c. Now, sometimes you can drop the absolute value sign if you're guaranteed to have something that was positive. So if that had said 5x squared plus 1, if my u was 5x squared plus 1, wouldn't matter what I plugged in for the x, my answer would always come out positive because after I squared it would have become a positive. So if you have something that's guaranteed to always be positive, then you could drop the absolute value signs. But if there's a chance that you could plug something in for x and get a negative, you have to leave the absolute value signs. If I wanted to do this one without a u substitution, what I would have done is, since I knew the derivative of 5x minus 1 was 5, if I could times something onto the top of the fraction to make that a 5, so since it's a 2, what could I times a 2 by to get me a 5? Okay, 2.5 or 5 halves. Okay, either way, 2.5 or 5 halves. So if I times by 2.5 on the top of the fraction to make that a 5, then if I wanted to keep this equivalent, if I times by 2.5, divide by 2.5. So then I could have put a divide by 2.5 right there. So as long as if I times the top of the fraction by 2.5, I have to times the bottom of the fraction by 2.5. And that was equivalent to doing 1 over 2.5. So I still had an equal fraction. And then from there, I would then have this as 1 over 2.5 natural log absolute value of 5x minus 1 plus c. And then if I did 1 divided by 2.5, that should be my 2/5 that I had in the other problem. So it is possible to avoid a u substitution if you want to figure out what you could multiply the top and bottom of the fraction by to get the top to be whatever the u prime needed to be. Okay, but I think a lot of times it's teaching-wise, it's easier to get students just to do the plain u substitution. But if that made sense to you, you are welcome to do this other method in red. Okay, so this 10x minus 1 over 5x squared minus x. Any ideas what that is? Exactly. This is already in the format u prime over u. If you did the derivative of 5x squared minus x, you would get the 10x minus 1. So since this is already a u prime over u, our answer is then just the natural log. Yep. And then plus, don't forget, add a constant labeled c. Now, the next one, x squared plus 1 over x cubed plus 3x, that one's not quite u prime over u. It almost is. So if my u was x cubed plus 3x, its derivative would be 3x squared plus 3. Correct. So you could do a full-blown u substitution, or recognizing the top needs to be times by 3. So if you times the top of the fraction by 3, yep, I would put a divide by 1/3 here. So the bottom of the fraction is really being times by 3 also, but then since it was a constant, I just pulled that one out. So now this is in the form u prime over u, because if I distributed that 3 into the x squared plus 1, I would get the 3x squared plus 3. So I now know that this would be 1/3 natural log absolute value of the denominator, which was x cubed plus 3x, and then plus c. If I finish this out as the u substitution instead of doing the timesing method that I just barely did. So if I had finished this one doing the u substitution, oops, my thing just froze on me. I would have, right here, I would have factored out the 3, so I would have written that as 3 times x squared plus 1 dx equals du. And then from there, I would have saw that I could divide by the 3. So then I would have had 1/3 du equals x squared plus 1 dx. And then the u substitution would have worked. That 1/3 would be the constant. And then the x squared plus 1 dx goes away and just became the du. The denominator, x cubed plus 3x, is the u, and then just put a 1 right there. So you see that we're going to end up with the same answer of 1/3 natural log. In that case, it would have been absolute value of u plus c, and then you would have replaced the u back in. So sometimes it's easier if you can recognize that you can just multiply the top and bottom by something to get the numerator to end up being the derivative of the bottom. But again, you could just do the full-blown u substitution. Okay, so on this next one, we have a little problem because the derivative of the denominator would be 3x squared plus 1, and we have a whole bunch of extra stuff on the top of the fraction. Any ideas what we might be able to do? Not give up. We keep trying. Okay, this is where in that little list of stuff it says try altering the integrand. So if you can't, a u substitution wouldn't work. If you can't find anything that works, try altering the integrand. I could try factoring, yes. I think factoring would work on that one. How could I factor the numerator? Let me go through this little hint. I'm pretty sure says long division, and then there is a way we could have factored or kind of used factoring. But if I did it as long division, I would divide by the denominator, x cubed plus. You should have had a little bit in secondary 3. We followed this division the same way you learned in elementary. So I'm going to take this first term underneath the root, the x cubed, and I divide it by this term outside of the root, the x cubed. So what is x cubed divided by x cubed? Good. So my 1 is going to go up here, and then whatever you have sitting up there, you times by the numbers in front, whatever you have in front of the division bar. So I have 1 times x cubed and 1 times x. So that would give me an x cubed plus x. And then in elementary, what would you do next? Subtract. I heard it over here. You would subtract it off. So I'm going to subtract that, and then, well, I need to finish up the, yeah, but that is going to be the derivative of that part. Okay, now I'm actually done with, well, almost done, because here where I have 3x squared, if I divided that by x cubed, I guess I could, but once this power right here is less than this one, then we usually just go to the remainder. So now I'm just going to say plus, and then put my 3x squared plus 1 over my x cubed plus x. So I can rewrite this integral. This integral is now the integral of 1 plus 3x squared plus 1 over x cubed plus x. So I still have my integral because I still haven't done any integration. All I've done is rewritten the integrand. Do you have a question? You're good? Okay, so now from here, I can do the antiderivative of 1. And what's the antiderivative of 1? Good, x. So that will be x. And now when I do the antiderivative of the fraction, what do we notice about that one? Good, u prime over u. So now I can just put natural log absolute value of the denominator, x cubed plus x, and then plus a constant. Now, there is another way I could have done that without doing it as a long division. I just thought it was good for you guys to see the long division. Another way I could have done that is I could have rewritten that integrand. I could have broken that into 2 separate fractions. One fraction, x cubed plus x. The other one would still have the x cubed plus x. And then I could have put, yeah, these ones on one, and then these ones on the other one. So then I'd have x cubed plus x. and the other one, the 3x squared plus 1. Yeah, that's nicer, but sometimes that doesn't work. So, so if it doesn't quite work that you could just like separate it like that, then long division works. And then that first fraction is then equivalent to 1, and then you just work it out like I did the previous one. Okay, so u being x plus 1, so then my du would be 1 dx. Okay, so now I'm going to have this little issue. Right now, if I try to use substitution, my dx becomes a du, and then my x plus 1 becomes a u, so I'll have a u squared, but my top of my fraction is still an x. What could I do to get rid of that x?
Solve for x.
Yes.
Then plug in u minus 1 for x.
Good. Okay, so solving for x, I would get x equals u minus 1. Plug that in. U minus 1 over u squared du. Okay, and then from here, I would just simplify that, break that into two separate fractions. So then I get u over u squared minus 1 over u squared du. Okay, so that first fraction, u over u squared, is the same as 1 over u. And we now know what that antiderivative should be, because that's in the format u prime over u, because the derivative of u would be 1. And then the 1 over u squared, though, that's not u prime over u. But these are the ones that we've been doing before, where you can bring it up to the top and just add a power times by the reciprocal. So you can treat the two separate fractions different when you're doing the antiderivative. So that second one, I'm just going to write it as negative u to the negative 2 du. So the antiderivative of 1 over u, that's the u prime over u format, so natural log absolute value of u, minus, now on this next one, I will add a power. So I'll get u to the negative 1 times by the reciprocal. So I times by negative 1, because the reciprocal is 1 over negative 1 is still negative 1. And then plus a c. So natural log absolute value of u, the negative, yep, it's a plus. And then I'm going to bring that u back down to the denominator. Yep, 1 over u plus c. And then I need to substitute back in what u was, which was x plus 1. So natural log absolute value x plus 1 plus 1 over x plus 1 plus my constant. There's my answer. Okay, so this page reminds us of the integration with trig functions. So remember, the antiderivative of sine gives us negative cosine, not positive cosine. I don't think we've seen, have we seen the yeah, we've seen the antiderivative of tangent. I can actually, no, I think this is the first time we've seen this one.
Yeah.
Okay, I can show you why the antiderivative of tangent is negative natural log of cosine. Exactly, yes, because tangent could be written as sine over cosine. And then this is, what's the derivative of u? I mean, sorry, what's the derivative of cosine? Good, negative sine. My top is a positive sign. So if I times that by a negative 1, then I can times by a negative 1 in there. So it's really timesing negative 1 on top and negative 1 on the bottom of a fraction. So now inside that integral, I have u prime over u. So now that's going to be 1 over negative 1 is just negative 1. Then I'll have natural log absolute value of the denominator, and then plus a constant, which is basically what we have right there. So these ones that have natural logs in it, that's because you can rewrite these trig functions in terms, make them a fraction, and then you can work things out. Okay, so this one right here, if I wanted to evaluate from 0 to pi fourths of root 1 plus cotangent squared x dx, first off, we don't have any integrals here with a 1 plus cotangent. But this is a Pythagorean identity. So if you guys have the paper that I gave you that had a photocopy of the front and back cover of your textbook, look under the Pythagorean identities. There's 3 Pythagorean identities. Okay, so this right here was just a Pythagorean identity, one of the 3 on your paper. So since I know 1 plus cotangent squared equals cosecant squared, I could do a substitution. So I could rewrite this as the root cosecant squared x dx. But now, since this cosecant is squared and there's a square root, they can cancel out. So I get cosecant x dx. And then we just look up to our handy-dandy rules up here, and I see what cosecant is. So I now know that this would equal negative natural log absolute value cosecant u plus cotangent u plus c. Yes, I forgot that this was a definite integral. Sorry, and I shouldn't have put u there. I should have put an x, because x is what my problem had as the variable. Okay, and then instead of doing plus c, since it was a definite integral, I'm actually not done. Instead of going plus c, I need to evaluate it from 0 to pi fourths. So I'll go negative natural log absolute value cosecant pi fourths plus cotangent pi fourths minus, now plugging in 0 into both of those, negative natural log absolute value cosecant 0 plus cotangent 0. Okay, so now using the unit circle at pi fourths, if I want to do cosecant, how do I find cosecant? What's cosecant the same as? 1 over what? Not 1 over cotangent. 1 over sine. 1 over sine. I just remember with the cosecant and secant, it's the opposite letter. So if cosecant starts with a C, its reciprocal starts with an S. That's what I use to remember. They don't start with the same letter. So the reciprocal of cosecant is 1 over sine. Sorry, cosecant is the same as 1 over sine. So my sine on the unit circle goes cosine comma sine. Here they're both the same number anyways, but the sine is the second value. So I want 1 over sine. So if I wanted 1 over this, I'd basically just flip the fraction. So that's going to be the same as 2 over root 2. Instead of root 2 over 2, I would flip it and get 2 over root 2. So I have negative natural log of 2 over root 2 plus, now cotangent. How do I find cotangent? What over what is cotangent the same as? Cosine over sine. Okay, so cosine over sine. Ordered pairs, root 2 over 2 is the cosine value. The sine value is root 2 over 2. So if I did cosine over sine, root 2 over 2 divided by root 2 over 2, 1 is the answer. Yep. Minus, actually this next one, the minus and negative can become a positive, natural log. Okay, so cosecant of 0. So cosecant, remember we just said that was the reciprocal of sine. So since my sine value is 0, what's the reciprocal of 0? It's not 0. 1 over 0, which is undefined. So this whole problem right here, I just barely got an undefined. I don't need to even finish anything else because this isn't defined. Can't do it. Okay, so this whole answer, undefined. It wasn't useless. We got a lot of nice stuff. A definite, since this was definite integral, I could check my answer in the calculator. Remember on your calculator, where do I find the integrals? Okay, math, and then arrow up or down until you find function integrate, so number 9. And then you would type in the original, first 0 to the pi fourths. And then you type in the original problem, and the original problem was the root. Yep, 1 plus. Now, how do I do a cotangent squared? How would I put that in?
We know that cotangent is there's 1 over.
Okay, so 1 over tangent x, and then I'm going to close that parenthesis and close that, and then I'll put the square outside of my big parentheses. Okay, and then dx over here. And then I do need to make sure I'm in radians and not degrees, otherwise I will get the wrong answer, but I'm in radians, so I'm good. And then my calculator's thinking. Okay, so it finally told me error. It says tolerance not met. Who knows? Either way, we can't do it. I love the antiderivatives with e's because it's e. Yeah, because the derivative of e to the x is e to the x. The derivative of e to the u is e to the u prime. Yeah, so if it's not just an x, then you have the u prime. So if this is just e to the x, its antiderivative is e to the x plus a constant. If it's in the form e to the u, then it's e to the u plus c. Okay, so, but we do need to do a little bit of u substitution because the derivative of the u. So right here, my u right now would be the 4x plus 2. So my u, oops. And then if I do the derivative of that, I get 4 dx. So the derivative of the u was missing from the problem. So I will divide by 4. And I will now rewrite this as 1/4 the integral e to the u du, just doing a u substitution. Or I could have times a 4 right here inside the integral, and then times a 1/4 in front of the integral, if you didn't want to do it as a full u substitution. But I was missing that constant of a 4, because I had to have the derivative of the u in my problem. Okay, so then that antiderivative will be 1/4 e to the u plus c, and then I just substitute back in what my u was. So I get 1/4 e to the u, which was the 4x plus 2, plus a constant. So when you're doing the ones with the e's, you do have to make sure that the derivative of the u is in the problem. Okay? If it's not, do it as a u substitution or times by a constant to make it be there. Okay, so the next one, what would be the u on the second problem? Good, negative x squared. So what is the derivative of negative x squared? Okay. So looking over here, I have a 6x dx. I need a negative 2x dx. So what if I wanted to do the multiply by something, what could I times by? I could times by negative 1/3, because I want to make the 6x become a negative 2x. So basically, it's like dividing by the negative 3, or times it by negative 1/3. On this one, I'll just go ahead and just do it as the u substitution. So I could go and say divide by the negative 2 here, so negative 1/2. And then that 6 I could pull out in front. So I pull out the constant of the 6. And now the x dx becomes the negative 1/2 du. So there's the negative 1/2, the integral, there's the du. And then I now have e to the u. And then 6 times negative 1/2 is negative 3. The antiderivative of e to the u is just e to the u plus a constant. And then I substitute back in what my u was, which was negative x squared plus a constant. Okay, so for number 3, what do you think my u should be? Good, 1/x, because I want it to be e to the u. So whatever that power is on the e should be your u. So with these e ones, yeah, I'll usually, I'm not going to say always, because someone will then come up with something that would be something different, but we'll just say like 95% of the time. Yes, 1/x is correct. Okay, now when I do the derivative, of 1/x, what's that going to be?
That's going to be the natural log of x.
If natural log of x would be if I was doing the antiderivative. I want to do the derivative. Okay. Yeah, so I'll bring the x up and have that as x to the negative 1. So yeah, du will be negative 1 x to the negative 2, which is negative 1/x squared dx. Okay, so now when you look at the bottom of this original problem, notice on the denominator I have an x squared and I have the dx. So the x squared, yeah, there's no negative. So I could divide the negative 1 over, or times by -1. It doesn't matter which way you do that. So now I know -1 du equals 1 over x squared dx. So now doing my, and that's this 2 that's right here, that 2 is just a constant, so I can just pull that 2 in front. So I'm going to have the constant of the 2, and then I'm going to replace the 1 over x squared dx with a -1 du. So there's my -1, the integral, there's my du. And then the e will be there, and then the 1 over x became the u, and then that x squared's gone because that became part of the -1 du. Yes. So then from here, 2 times -1 is -2. The antiderivative of e to the u was what? Perfect. E to the u plus a constant labeled c. Okay. So then I get -2 e to the u, and u was originally 1 over x plus a constant. Okay. So on this one right here, what should my u be? Cosine x. And what is the derivative of cosine x? Negative sine x, yes.
And then you take out the negative with the 3 outside.
Good. Okay, so the 3 constant goes in front, times by the -1, and then the du. Okay, so that sine dx is gone, and then I just have e to the u left. So I have -3 e to the u plus a constant, and then substituting back in what the u was, which was cosine x, plus a constant labeled c. Okay, so if we want to use our calculator to find this, so if f, capital F of x, is the antiderivative of e to the x squared. So meaning if you did the integral of e to the x squared, you would get capital F of x. That's basically what it tells us. Now, the reason we're doing it on the calculator is because I can't do u substitution on this one, because u would be the x squared, and the derivative of that would be 2x, and there's no way I can get a 2x over there. Okay. So using the calculator, where it tells me f of -1 is 2, and I want to find f of -2, basically those numbers that are right inside here, those tell me the numbers that I can put on the limits of the integrand, because those are the x values. And then the answer you get out of like 2 and what you're trying to find, those are the y values. And then when we do this, we'd like to go lowest number to highest number. Lower number on the bottom of the integrand, higher number on the top of the integrand. So I would put the -2 down here because it's the smaller number, and then the -1 up there because it's the bigger number. Now, the fundamental theorem of calculus said after we do the antiderivative, remember you plug in the top number, then you go minus, plug in the bottom number. So I know this antiderivative is f of x, but then if I plug in the top number, so we plug in the top number minus the bottom. Okay, so if I plugged in the top number, I would have f of -1 minus, plug in the bottom number, f of -2 equals, now this is where the calculator comes in handy. I could do this part of the problem in the calculator and find out what that number is. So on the calculator, I just do math and then whatever one is function integrate. Math 9, it looks like. And then I type in from -2 to -1. And then e raised to the x squared. And then type in the x over here for dx. Okay, so now from here, I type in 14.98997. Now, the question wanted us to find what f of -2 is. I know what f of -1 is. They told us that.
2.
Yes. So I'm going to replace this right here with the 2 that they told us. And then I'm just going to solve the equation for f of -2. So I'm going to -2 to both sides of the equation. So I now know negative f of -2 is going to be 12.98997. Yep, good. So times by -1 or divide by -1, whichever way you prefer to do it. So I now know f of -2 is -12.98997. Again, on the AP test, you only have to go to 3, so you could go -12.989. That would be truncating it, or you could round it. Rounding would be -12.990. And I would put that 0, so you have 3 spots. Yes. So if the number ended naturally at 2 spots, then I don't think you'd have to put a 0 for the third spot, but there were more numbers, so if you rounded it, I would keep that 0 for the last spot. Okay, so this next one, it's done the exact same way. Okay, so this one I would do the same thing. We know f is the antiderivative of that root, so I know if I did the integral of this, the answer is f. It wants me to find what f of 5 is, and it told me what f of 1 is. Again, the 1 and the 5 are x values, so I can put those on my limits. And you do the lower limit number first. So I put the 1 first, and then I put the 5. And then I know the first fundamental theorem of calculus says when you do the antiderivative, you plug in the top number minus the bottom number. So the antiderivative was f, so then I can plug in the top number minus plug in the bottom number. And then on your calculator, you just input that on your calculator. So again, you go math, number 9, type in the limits first, and then the root. On yours, you do the lower first, and then the upper. Okay, so then I get 25.8655. And then I know what f of 1 is. They told me f of 1 was 3. That's my initial condition. Good, add 3, because it was saying a -3. So now I know f of 5 is 28.8655. Again, it never hurts to give more than 3. Just don't give less than 3.